Okay, this is section 3.3, evaluating limits analytically. Analytically is another word that you can think of for algebraically. In this lesson, we're going to be evaluating limits. We're going to be finding the answers to what a limit is, which is a y value. However, we will not have a calculator with us to make a table, and we will not look at a graph to see the picture of what the y values are approaching. So let's review what we know about limits so far. The limit of a function is concerned about the function near the x value in question. It is not what is happening at the actual x value. F of a is what happens at our actual x value. And this is a pre-calculus question. Now, it turns out that what happens near the x value is sometimes what's actually happening at the x value. And actually, this happens a lot of the time. In this case, the limit as x approaches your number in question, which I'm just calling the letter a here, of the function is actually what's happening at the function. And this is our very first trick for evaluating limits, is we hope that this happens. And so our very first strategy is right here. We're just going to plug in or substitute a, which is this number that x is approaching, in order to evaluate the limit. Always try that first. And what I have written here is a step-by-step method for what we're going to do to solve limits. The very first step is to plug in, and here I've changed the letter A to the letter C. So plug in A. Plug in A. That's an A. Once you plug in A, you're going to analyze what your results are. We have three possibilities from plugging in A. The first possibility, which is letter A, but the first possibility would be a nice simple answer. That is the case in which what's happening near the function value is what's happening at the function value. When this happens, a special thing has occurred. The function is called continuous, but we'll have a whole section on being continuous. And that's your answer, and you're done. Okay, so that's easy. You're going to have a lot more difficult questions in which that's not the case. The second option is that you get a number divided by 0. Back before texting was so popular, or Twitter or whatever, hashtags were also symbols that we used for a number. So I'm using the pound symbol. It's also another name for this symbol, which you all know is hashtag. I'm using that hashtag or pound symbol to denote any number. So if you get a number divided by 0, then we're going to get an infinite limit. Technically, we don't exist. Again, this is going to be a whole separate lesson. What you're going to see most often in today's lesson is that you get 0 divided by 0. Now, 0 divided by 0 is something very special. 0 divided by 0 is what we call indeterminate. An indeterminate number. That does not mean that I know the number, but it does not mean that the number exists. It does not mean that we have an answer. We could also not have an answer. We could go revert back to case B, or we could revert back to case A, either one of those two. But what's happening in number 1C, which is where we're going to live mostly today, is that we have an indeterminate answer. And in that case, we need to try to simplify. It means work harder. This means work harder. And we're going to do 5 examples today in which I show you all of the techniques of working harder. Essentially, we're just going to simplify. In one case, I'll show you how to simplify by getting a common denominator. In another case, we're going to factor and cross off. Multiplying by the conjugate is going to be another type of question. And then essentially, once you've simplified, you're going to cancel the 0 over 0. That's what's happening in the simplification. You're going to cancel the 0 divided by 0 part, and then you're going to retry. That's what's happening. Okay, so let's do some examples. Our first example, we have the limit as x approaches 2 of x minus 3 over x plus 2. And if you look back up at the method I give you for how to evaluate a limit algebraically, the very first step is to plug in the number in question, a. All right, so in this example, my number in question, x is approaching the number 2. So I'm going to simply replace x with the number 2. When I simplify this, I get negative 1 divided by 4. That is a number, and that is my answer. I do not want you to write crazy things when you get an answer. You can simply write the number and circle it like I've done, or you can write the limit as x approaches negative 2. You have to have a function here, and then is negative 1/4. I don't want you to write LIM without a function. So either one of these circled quantities is appropriate for displaying your answer. Okay, let's move on to number 2. It's not going to work out so nicely in number 2. I'm going to follow my method for solving limits algebraically. It worked last time. The first step is simply to plug in my number. Um, Hopefully we'll get a nice one again. It's not going to happen though. All right, so I replace x with 2. And when that happens in the numerator, I get 4 minus 4, and in the denominator, I get 2 minus 2. This is 0 divided by 0, and 0 divided by 0 is called indeterminate. That is indeterminate. That means work harder to determine what the answer is. In this case, if you look closely at my function that I'm taking the limit of, the numerator is a difference of squares. And we all remember from Mrs. Pyle's class that differences of squares factor very nicely. And so I'm going to go ahead and factor that numerator. Oh, look at that. Now I have a common factor of x minus 2. I'm going to cancel that common factor of x minus 2. This leaves me with x plus 2. Now I'm going to, so now I have, following my strategy, I plugged in my number. I got 0 divided by 0, which was indeterminate. So in that case, I went on to step 2, which told me to simplify. And so I did. I factored and crossed off. And now I'm going to try to plug in again. And so here I am. I have the limit as x approaches 2 of x plus 2. If I plug in again, I get 4. That's my solution. The limit is 4 there. Okay, so some of you might be a little concerned about the fact that I'm writing a lot of information, but I'm not writing too much information. What I have written here is limit as x approaches 2 of the function, and then I canceled and I wrote limit as x approaches 2 of the function, and then I plugged in and I stopped writing limit as x approaches 2. So where do I have to write this guy, this limit as x approaches 2 thing that I'm shaking around here? You need to write it in every step, until you have your answer. And then you don't write it anymore because you already solved the limit. So the limit is an action, it's an operation. It's telling you to do something, to evaluate your function, sort of, to evaluate the limit of your function. Once you have your answer, you no longer write to do the limit because you have already done it. So I will write it properly throughout this entire lesson, and you need to write it properly as well. All right, we're going to move on to question number 3. In question number 3, I have square roots. So it's the limit as x approaches 0 of a difference of radicals over x. Notice what happens if I plug in 0 to x. I get square root of 2 minus square root of 2 over 0. This is 0 over 0. Oh no, that is indeterminate. And so that means I'm going to work harder. I do not see anything to factor, and so I have, in truth, I really don't have anything to factor, but I'm going to use the method of multiplying by the conjugate. So the conjugate, if you remember from our complex numbers um, work, is when you have the same exact expression, it's a binomial, you have two terms, but instead of, in this case, we have a minus sign between them. Instead of a minus sign, we're going to have our two terms, but with the opposite sign between them. So since this originally was a minus, I'm going to change it to a plus. Now, you can't just multiply the numerator by whatever you want, but you can if you multiply the denominator by that as well. And so that's what we are doing here. Multiplying by the conjugate is the coolest trick because it turns foiling into fulling. We're no longer going to foil, we're going to first last. And that's because your outside and inside will be the exact same product in opposite signs, and so they will cancel. And this works lovely with radicals because it also eliminates radicals. So in my numerator, when I FOIL 2 plus x, radical 2 plus x minus radical 2 with radical 2 plus x plus radical 2, I get 2 plus x minus 2, which is lovely. Now, here's your trick. When you multiply by the conjugate, I want you to multiply out the part in which you multiplied by the conjugate. So if your numerator got conjugated, that's who gets multiplied out. The other part, in this case the denominator, do not multiply that out because you will not be able to simplify properly. What's going to happen here? These 2's are going to cancel. Yay! And I have an x in the numerator. I do not want to have distributed the x in the denominator because then I might miss the cancel. And here I'm canceling my 0 over 0 indeterminate part. Wahoo! And I can try to reevaluate my limit now and get a nice answer. And that is going to happen. Oops. So when I replace my x with a 0, hold on. I randomly changed this 2 plus radical 2 plus x to a 2 minus x. Okay, so when I replace my x with 0, I get 1 over radical 2 plus radical 2. This is 1 over 2 radical 2. There is my solution, 1 over 2 radical 2. Okay, I have not forgotten this example number 4 up here. Let's move on to him. Okay, in this example, I have a complex fraction, which is fractions inside of fractions. So you can see that my numerator is a fraction as well. Okay, so I'm going to go ahead and try to replace x with 0 and hope I get an answer. Oh dear, it did not happen again. I got 0 over 0. So now what's my trick in order to simplify this? I can't cross off. I don't have radicals, so multiplying by the conjugate is not going to help here. But what is going to help is to simply simplify this awful complex fraction. So my denominator was x, and he's just fine. But in my numerator, I'm going to get a common denominator. My common denominator of my numerator would be the product of x plus 2 and 2. So 2 times x plus 2. In the first term, 1 over x plus 2, I had the x plus 2 already in the denominator, so I multiply the numerator by 2 as well. And in my second term, I needed to multiply my denominator by x plus 2, so that's what I multiply my numerator by as well. I'm going to be very careful here because I'm supposed to minus the entire second term, which means I need to minus both x and 2. Things will not cancel if you do not distribute negatives. So we need to remember to distribute negatives. Okay, my lines are getting wonky here. So my denominator, let me write my denominator in green. My denominator was x. I have done nothing to him. I'm just rewriting him every time. My numerator, I got a common denominator for. And so now I'm going to simplify that, and I'm going to distribute this negative. So this turns into a negative x, and then the denominator of my numerator is 2 times the quantity x plus 2. And so now I have 1 simple fraction in my numerator, negative x over 2 quantity x plus 2. And my denominator, who's x, is really x over 1. And when I divide by x over 1, that's the same as multiplying by 1 over x. So this green denominator, x over 1, dividing by x over 1 is multiplying by 1 over x. And lo and behold, woohoo, the x's cancel. And I am left with negative 1. Whoops. Oh, this is a no-no. I have to rewrite the limit because I haven't evaluated it yet. Negative 1, because when the x cancels, it divides. And when you divide something by itself, you get 1. Okay, so I have the quantity. I am evaluating the limit now as x approaches 0 of negative 1 over 2 times the quantity x plus 2. Now I don't have to write the limit anymore because I am plugging in 0 for x and evaluating the limit. And my answer is negative 1/4. I've got one more example for you, and it's a doozy. Um, this is the language that the book uses very commonly. It has what seems like a lot of delta x, or x's in it, but it really has two different letters, okay? It has the variable x, which you see here in blue. The variable x um, is actually going to stay throughout this whole problem, and it's going to be part of our answer. Our limit is not for x. It's actually for delta x. This is an important concept because we're going to see this again when we get to calculus and tangent line problems. In tangent line problems, remember, we use we actually use secant lines, and to find the slope of a tangent line, we do a slope of a secant line, but our second x point is really close to our first x point. So if you take the difference in them, which is a delta x, you want that difference to essentially be 0. So we're looking ahead to that problem here. But you can do this part now. So delta x, he is in green. I'm going to highlight him in green. And he is the guy who is approaching 0. So when I evaluate this limit, I'm going to replace 0, or I'm going to place 0 in the place of delta x. I have nobody to put in x. X does not get evaluated. So this will be x plus 0 cubed minus x cubed over 0. Let me highlight again. The delta x parts are who are approaching 0. X is just a variable, and I am not doing a limit of x. I'm doing a limit of delta x. And so again, x is just going to carry through because he is not approaching 0. It's delta x who is approaching 0. Okay, so when I evaluate this, I get x cubed minus x cubed, because x plus 0 is x, and then that quantity is cubed. And so x cubed minus x cubed is 0. And I have 0 over 0. Again, I'm indeterminate. All right, this one's actually pretty simple to evaluate. The only thing to worry about is keeping track of who's an x and who's a delta x. The way we're going to evaluate this one, or to simplify this, because again, I got an indeterminate. So the way I'm going to evaluate this is this cube, I'm just going to evaluate the cubic expression. Okay, so when I cube x plus delta x, I have to FOIL twice. So I'm not going to go through all of that math. I just know that it's going to turn out as x cubed plus 3x squared delta x plus 3x, and now this time it's delta x who's squared. I put parentheses around the delta x because I want you to remember he's his own thing. It's not a delta times an x. It's its own quantity, delta x. And then plus delta x cubed. So here I didn't put the parenthesis because it's not necessarily needed. Now I'm recopying this minus x cubed. This minus x cubed. He got recopied here. And I just FOILed the x plus delta x twice because it was cubed. And then my denominator is a delta x. So notice what happens here. I have like terms, but only one set. I have an x cubed and a minus x cubed, and so those will cancel. Once I cancel those, let's look at what's left. Oops. All right, let me make this nicer. The limit as delta x approaches 0, and in my numerator now I have a 3x squared times a delta x, and delta x is approaching 0, plus 3x times delta x squared, and it's the delta x who's approaching 0, plus delta x cubed, all divided by delta x. Now, I don't want to evaluate again here. I can just see by glancing that if I replace my delta x with 0, I get lots and lots of zeros. This will result in 0 over 0 still. I have not canceled the 0 divided by 0 part. But do you see that there's a delta x in every term of the numerator? I can factor that delta x out, which is what I'm going to do now. If I factor a delta x out, I'm left with 3x squared from my first term, 3x from the second term, and then one delta x that didn't get factored out because that was a squared. And then in my final term of my numerator, that delta x cubed becomes a delta x squared because I factored out one of the delta x's, divided by delta x. Well, wahoo, here is where I'm canceling 0 divided by 0. So my limit is the limit as delta x approaches 0 of 3x squared plus 3x delta x plus delta x squared. And the delta x is the one who is approaching 0. So these green delta x's I'm going to replace with 0. And I get the answer 3x squared plus 3x times 0 plus 0 squared. The delta x's I replaced with 0. X, he's just hanging out this whole time. Nothing happens to him. He just hangs out, and you operate on him because he's there. But it's the delta x who's approaching 0. He's the one I replace with 0. This becomes 3x squared because 3x times 0 and 0 squared is 0. And so your answer has an x in it, and the answer is 3x squared. And this concludes 3.3, solving limits algebraically.